Hello everyone, welcome back. This particular video is going to focus on conjugate addition reactions. And the specific example for a conjugate addition reaction that we will later look at is a Michael reaction or a Michael addition reaction here. Now, before we get into the Michael reaction itself, we have to first understand what conjugate addition means. Now, conjugate addition is a reaction that is very specific to a class of compounds, alpha beta unsaturated compounds. Now, they can be alpha beta unsaturated ketones, they could be alpha beta unsaturated esters, they could be alpha beta unsaturated amides, anything. So essentially for our discussion here, what we're going to focus on is the reaction of a nucleophile with an alpha beta unsaturated compound. And again, like I said, when we say the compound here, think about alpha beta unsaturated ketone, aldehyde, amide, ester. So any of those classes of compounds, when they have an alpha beta unsaturation, they would participate in this reaction. So now, alpha beta unsaturated compounds, we've seen this prior in the Aldol reaction. One way to synthesize an alpha beta unsaturated carbonyl compound, like an aldehyde or a ketone, is through an Aldol reaction. So these compounds, they have unsaturation or a double bond between the alpha and the beta carbon. Okay, so with respect to our functional group, that's our alpha carbon and that's our beta carbon. So there is an unsaturation there. Now, if we are trying to think about the reaction of these compounds with nucleophiles, that means this compound is going to behave as an electrophile. Okay. The alpha beta unsaturated compound, this is going to behave as an electrophile. Okay, so the big question is then, where is the electrophilic site in the alpha beta unsaturated compound? Okay, it's going to behave as an electrophile. So the question that we're trying to answer here is, where is the electrophilic site in the alpha beta unsaturated compound? Okay, question mark. Now, when we look at this compound here, we can determine the electrophilic site by identifying which site or which atom is lacking electron density, is electron deficient. So, and resonance can help here, okay? So if we draw some resonance forms for this molecule or this generalized compound, that's one resonance form of the molecule, but we can draw a resonance form by pushing the electrons up. That would be the simplest resonance form that we can draw. So the second resonance form that we're going to get is going to have a positive charge on that carbon, and the oxygen is going to have a negative charge. So that's one possible resonance form. So these are all resonance forms. Now we can draw an additional resonance form by moving the pi bond. So we can take the double bond here and move it here, because that positive charge is allylic to this double bond. So we can move the electron pair from that double bond, and that would give us an additional resonance form here. So we've got Z, we've got double bond over there, and the positive charge is on this carbon. And again, let's keep our labeling. So this was the alpha carbon and this is the beta carbon. This is alpha and this is beta. And now, based on these resonance forms, if you were to determine the electrophilic site, we can see that there are two electrophilic sites in this molecule, two sites that are electron deficient. One is the carbonyl carbon. That carbon there, this is electrophilic. And second is the beta carbon. That's also electrophilic based on the resonance form. So that means for an alpha beta unsaturated compound, there are two electrophilic sites. One is the carbonyl carbon and the other one is the beta carbon. They're both electrophilic. And what that means is when you react it with a nucleophile, the nucleophile now has, in principle, it can go and attack the carbonyl carbon, or it can go and attack that electrophilic carbon. Let's see what difference it makes and what sort of nucleophiles do the attack at the carbonyl carbon and what sort of nucleophiles attack at the beta carbon. Now, these attacks and the resulting products, they have different names. One is called the 1,2 addition. Okay, 1,2 addition. And this is when the nucleophile attacks the carbonyl carbon. Okay, so the nucleophile attacks the carbonyl carbon. Then it's called a 1,2 attack. And an example of a nucleophile, such a nucleophile, is a Grignard reagent. Okay, Grignard reagents are very strong nucleophiles, and they go and attack the carbonyl carbon. Okay, so these are very strong nucleophiles. In fact, very strong nucleophiles. So if you have an alpha beta unsaturated compound and you react this alpha beta unsaturated compound with a Grignard reagent, RMGBr, magnesium is positive, the nucleophilic R group here goes and attacks the carbonyl carbon. And very similar to a nucleophilic, well, this is a nucleophilic addition here, very similar to what we saw in the mechanism of nucleophilic addition. That double bond pushes up to give us an intermediate. And this is a tetrahedral intermediate in some sense. Okay. Now, what happens after this would actually depend on the nature of the Z. So I think for our purposes, what we're going to do here is let's substitute this with an H here to be very specific. Okay, so that we know that we're working with an alpha beta unsaturated aldehyde, because if we were working with a carboxylic acid derivative, then the outcome of this tetrahedral intermediate is going to be very different. But let's say if you're working with an alpha beta unsaturated aldehyde, the nucleophile attacks the carbonyl carbon, gives you a tetrahedral intermediate. That's the first step. And then a subsequent step, what we will do is we will do a workup, or we will protonate this oxygen. So the oxygen here is going to get protonated, and it would give us a product where we have OH, we have H here, and we have the R group here. Now, if you look at the product here, what we did is we added two components to atoms that were related to each other as 1 and 2. So if I start, let's say, counting from this oxygen is atom 1, and this carbon here is atom 2. So this is 1, this is 2, and this is 1, and this is 2. So essentially what we did in this reaction here is we added an R group to the carbonyl carbon, and we added a hydrogen to the oxygen. And the atoms that these groups added to, the R group and the hydrogen, they are related to each other as 1 and 2. That's why this is called a 1,2 addition. That means you're adding two atoms that are adjacent to each other. In fact, they are bonded to each other, okay, that are engaged in a double bond. You're adding to such atoms. So that's why this is called a 1,2 addition. So we will call this the 1,2 addition product because we're doing a 1,2 addition here. Let's look at the next possibility or the other possibility here. This possibility is called the 1,4 addition, and this is also called the conjugate addition. The 1,4 addition or the conjugate addition. Now, this involves attack by the nucleophile on the beta carbon. So now the nucleophile is attacking the beta carbon. And a good example of a nucleophile would do something like this is a Gilman reagent. Okay. So Gilman reagent. Gilman reagents, recollect, are organometallic reagents similar to Grignard reagents. These are copper-based, so R2CuLi. But they are not as reactive as a Grignard reagents. They are not as strong nucleophiles. The R group here is not as strong of a nucleophile as the R group in a Grignard reagent. And the Gilman reagents are less reactive. So compared to this, the Grignard reagents, we can say that these are less reactive, which means they are a little bit more stabilized, okay? Because that's how it happens in reactions. When something is not stable, it's going to be very reactive. But if something is stabilized relatively, then it's going to be less reactive. So Gilman reagent is an example of something that's less reactive. So it's a bit more stabilized here. So what happens with a Gilman reagent is if we use the same alpha beta unsaturated aldehyde now, the one that we used earlier, the Gilman reagent will react with this. So this Li plus, that's sort of a structure of what a Gilman reagent looks like. You have two R groups connected to the copper and then the lithium. So essentially what happens is the R group from here comes and attacks the beta carbon now. Okay, it attacks the beta carbon. And when that attack happens, the pi bond opens up, goes into the space between the alpha carbon and the carbonyl carbon. And simultaneously, the double bond here is pushed up. Okay, so the R group attacks the beta carbon. And so the product or the intermediate that we're going to get here would be O minus H, the R group added here, and we have a double bond there. This is the beta carbon, this is the alpha carbon. Okay, and now subsequently, if we do a protonation of this intermediate that we've got, the oxygen will get protonated, electrons go to the oxygen. Hydrogen, double bond, and we've got an R group here. That is what we are going to get. Now, if you look at the structure here, and if we use a similar numbering scheme that we used in the first example, we start with the oxygen. This is 1. The carbonyl carbon is 2. Alpha carbon is 3, and the beta carbon is 4. So we have 4, 3, 2, and 1. Got 1, 2, 3, and 4. So if you look at this product now, the two groups, the R and the H, they added two atoms that are related to each other as 1 and 4. Okay, they're about 3 bonds away from each other. So this product, therefore, is called the 1,4 addition product. And that's why we say this is a 1,4 addition, and the other name for it is a conjugate addition, because this is a reaction of a conjugated system. If it were not an alpha beta unsaturated compound, which is actually a conjugated compound, you would not see this reaction. Now, this product that we made here, the 1,4 addition product, is not the final product here, because recognize that this structure that we have here is an enol. Okay, it's an enol, it's a vinyl alcohol. And what that means is, under the acidic conditions that we are in, it's going to quickly tautomerize to the more stable keto form. So the final product that we are going to get is going to be R over here and the aldehyde back. So the enol would tautomerize into the keto form, and this would be our final product from this process. Okay, so that's the comparison of a 1,2 addition, or what a 1,2 addition is, comparing it to what a 1,4 addition is, and what circumstances would lead to their formation. Now, the Gilman reagent is not the only nucleophile that is stabilized, or a weak nucleophile that would undergo a conjugate addition. There are other reagents that are suitable for doing this, and that's what would lead us into the Michael reaction. Now, enolates, as we know, are good nucleophiles, and they can actually participate in the conjugate addition reaction, or the 1,4 addition reaction. Now, for enolates of simple compounds, so for example, if we have a compound which has only one carbonyl or acyl group in it, you can react this with a base and you can generate an enolate. Okay, you can get the enolate where you have the lone pair on the alpha carbon, which is nucleophilic. Now, these enolates, these are stabilized by resonance, because recollect that they can do resonance. And so we can draw an additional resonance form for these enolates. So such enolates, when they participate in a conjugate addition reaction, so if I react such an enolate with an alpha beta unsaturated compound, we will get a mixture of 1,2 addition and 1,4 addition products. So we'll get the 1,2 addition product, and we will also get the 1,4 addition product. So we get a mixture of products here, because the enolate here is a strong nucleophile, but it's also resonance stabilized. So it is strong, so it does the 1,2 addition, but it is stabilized to some extent, so it is also able to do the 1,4 addition. So we do not have like a good control here. We cannot do this selectively where we choose one addition over the other addition. So these are enolates that are stabilized by resonance, and we can call these singly stabilized, because there's one additional resonance form that we can draw for these enolates. On the other hand, enolates of compounds where the alpha carbon is between two keto groups, when you treat these with a base, so when we treat this with a base, we are going to get the enolate corresponding to it. And we have the lone pair there. And this enolate now, it is stabilized by resonance, and it can be stabilized by resonance to the right, or it could do resonance to the left, basically saying that it can use both of these carbonyl or the keto groups for stabilizing this negative charge. So this is a doubly stabilized enolate. And such enolates, when they react with alpha beta unsaturated compounds, they give selectively 1,4 addition product. Okay, so we get selectivity here. We only get the 1,4 addition product in this case. So this reaction here, which involves the doubly stabilized enolate reacting with an alpha beta unsaturated compound, this reaction is called the Michael reaction. Okay, so this reaction is the Michael reaction. And the enolate or the nucleophile, this is what serves as the nucleophile in the reaction. The enolate or the nucleophile is called a Michael donor. It's called a Michael donor. And the alpha beta unsaturated compound, which is basically the electrophile in this reaction, this is called the Michael acceptor. Okay, that's called the Michael acceptor. So we have a Michael donor and we have a Michael acceptor. Essentially, another way of referring to the nucleophile and the electrophile in these reactions. Now, the doubly stabilized enolates, the Michael donors, there are several of these, in fact, several varieties. So we can imagine an enolate which is stabilized, doubly stabilized by 2 ketones. This would be a good Michael donor. It does not have to be 2 ketones. It can be 1 ketone and 1 ester. That would also be doubly stabilized. Or it could be 2 ester groups that give us a doubly stabilized enolate. But even that's not limiting here, because other groups can also stabilize. So if we have like a nitrile, this enolate can also be stabilized by the double bond O, the keto group, as well as the nitro group. So that would also serve as a Michael donor. In fact, just a nitro group here, that would also serve as a Michael donor. So any scenario where this negative charge in the enolate can be stabilized by more than one group, that would give you a Michael donor here. Okay. Michael acceptors, on the other hand, are alpha beta unsaturated compounds. So they can be alpha beta unsaturated aldehydes. So we could have Michael donors where they are alpha beta unsaturated aldehydes. We could have Michael donors where we have alpha beta unsaturated ketones. We could have we could have alpha beta unsaturated esters as Michael acceptors. We could even have alpha beta unsaturated amides as Michael acceptors. It could be an alpha beta unsaturated nitrile that can be a Michael acceptor. So any situation where you have an alpha beta unsaturation to a functional group, that would count here. They can all serve as Michael acceptors. Okay, so the specific case where you have a doubly stabilized enolate, which is the Michael donor, reacts with an alpha beta unsaturated compound, that's the Michael reaction here. Let's look at some examples of a Michael reaction or a Michael addition. So we have two examples here. In the first example, we have an alpha beta unsaturated compound reacting with a Gilman reagent, which is a good Michael donor. It is a stabilized nucleophile. So here we have this compound. There's alpha and beta, and you can see there's alpha beta unsaturated compound. So when this compound reacts with diethyl copper lithium, so or lithium dialkyl cuprate here, so it will be lithium diethyl cuprate. Okay, we have two ethyl groups on this lithium, and we have plus there. So the ethyl group here can go and attack the beta carbon. Okay, the ethyl group attacks the beta carbon. The pi bond moves to the space between alpha and the carbonyl, and the double bond opens up over there. And the intermediate that we are going to get here is going to be let's try to draw it exactly the same way. So we have that alpha and then O and methyl. This is the alpha carbon. This is the beta carbon. On the beta carbon, we would have another ethyl group now. So we've added another ethyl group to the beta carbon. So this is the nucleophile that came in. There should be a double bond between the alpha carbon and the carbonyl carbon and negative charge on that oxygen. So that would be the intermediate after our first step. Next, we are going to protonate it. So under acidic conditions, the O minus here gets protonated. And so we will get a product. We have OH. There's an ethyl group at the beta carbon. So this is beta, this is alpha. We have a methyl group, and there's a double bond over there. And notice what we created here is an enol. And under acidic conditions, the enol is not going to be the stable form. So it will quickly tautomerize under acidic conditions. The mechanism of keto-enol tautomerization under acidic conditions was discussed in a separate video. So please refer to that video if you're confused about how this works. But the keto-enol tautomerization happens, and essentially what we've been seeing throughout is that the double bond here moves to the space moves between the carbon and the oxygen, and the hydrogen from there comes to the alpha position. So essentially what we would get as our product here is going to be double bond O over there. Like that, and we have an ethyl group here. So the double bond moved to between carbon and oxygen, and the hydrogen came to the alpha carbon. So this is alpha, this is beta. So essentially we added the beta, the ethyl group to the beta carbon, and our product is going to be that, which is the Michael addition product here. So we've done an addition reaction here. Okay, so that will be our final product that we get from this reaction. Let's look at a slightly more complicated example here. Again, it's not complicated because it's difficult, it's just a bigger molecule, so we're going to see it again. You start with deprotonating this compound, okay, which is a beta dicarbonyl compound. So we react this with the base with sodium ethoxide. We are going to deprotonate the alpha hydrogen. And there are 2 alpha hydrogens here. One of them would get deprotonated. The electrons would move over there. So we get the enolate, negative charge here. Okay. Now, notice that this is a Michael donor because it is a doubly stabilized enolate. And so now we react this enolate with this compound, which notice is an alpha beta unsaturated compound. Okay, so it is an alpha beta unsaturated compound. So essentially what's going to happen is the nucleophile here is going to go and attack the beta carbon. And when it attacks the beta carbon, the double bond here moves to the space between alpha carbon and the carbonyl carbon, and the double bond opens up. And so the intermediate that we're going to get now will have a single bond here. The oxygen would have a negative charge. There should be a double bond between the alpha carbon and what was the carbonyl carbon. And on the beta carbon, we should have this nucleophile connected through that alpha carbon. So the alpha carbon is connected to the beta carbon here. This is the alpha of the alpha beta unsaturated compound. Maybe we can label this as alpha prime. And it is connected to the alpha prime carbon of this nucleophile here. And so we should have a double bond O, keto group, and we should have an ester group. So we're going to get that. And when we do the protonation, which is basically the third step here, so that's the second step. So the oxygen here gets protonated, electrons move over there. We will get an alcohol over there, but more specifically, it is an enol because it's a vinyl alcohol. Have double bond O, ET. Now, under these conditions with heat, you can potentially hydrolyze that ester also. Okay, so you can push the reaction in that direction. But if we focus on the Michael addition product here, if we focus on that for some time, now this enol that we made, this is the enol form. The enol form would quickly tautomerize to our product, which is going to be the keto form, double bond between the carbon and the oxygen, single bond all over here, and the beta carbon is connected to the keto group and the ester group. And as I mentioned, under these conditions, if the conditions are appropriate, it is possible that your ester would undergo a hydrolysis to give you a carboxylic acid. So that's possible. And there are other possibilities because then once it undergoes hydrolysis, if you heat it, what you've made is a beta keto acid, which can undergo a decarboxylation. So there are a lot of possibilities for making functionalized molecules or variably functionalized molecules here, but we'll just leave it here for now. Okay, we're going to assume that there is no ester hydrolysis going on, but that is a possibility. So keep that in mind, that this ester group can undergo hydrolysis, and you might eventually just end with a carboxylic acid where there is an OH group over there. So I hope you find the discussion on the conjugate addition, the introduction of Michael donor, Michael acceptor, and the solved examples useful. Bye.